Hi, and welcome back to the online physics lessons. Today we're going to be looking at electrical power, and we're going to be solving some selected problems from the packet. Electrical power is the rate of doing work, but can be expressed in terms of current, voltage, and resistance alternatively. On the reference table, you will find three expressions under equation E7. Power equals current times voltage, current squared times resistance, and voltage squared over resistance. Work and energy formula, E8, is nothing more than the top group multiplied by time. You'll notice that each one of these expressions has a time value multiplied by it because power times time is work and energy. Power itself is the rate of doing work. All right, let's get started. Here in problem number 3, a light bulb operates at 120 volts and draws a current of half an amp for 240 seconds. The power rating of the light bulb is, so when you see the words power rating, you know you're dealing with wattage or watts, meaning the amount of watts. So I know I've been given 120 volts and I have half an amp. So even though they give me the time here, I know that the P equals V times I formula only needs volts times amps. 120 volts times half an amp gives me 60 watts. That's a 60 watt light bulb. All right, let's take a look at the next one. In problem number 5, an operating 75 watt lamp is connected to a 120 volt outlet. How much electrical energy is used by the lamp in 60 minutes? Always remember, whenever you're given a time in minutes, you usually best to convert it into seconds right away. 60 minutes is 3,600 seconds. Now, since they're asking you for the energy, and energy is in joules, you know that energy is power times time. Since 75 watts was given as the power and 60 minutes or 3,600 seconds was given as the time, you multiply power times time and you get 2,700 joules. This is very important that in this part you substituted time in seconds, not in hours, because you will get the incorrect answer if you put time in the wrong unit. All right, let's take a look at the next one. In problem number 6, an electric motor draws 150 amps of current while operating at 240 volts. What's the power rating? So if they ask for power, you want wattage or watts. So you look for a formula that has the given variables, in this case, current and volts. So that's the PIV formula. Power equals V times I, 240 volts times 150 amps. So a volt amp is actually a watt. A little later on in this video, we're going to show you how all the electrical units work. Let's move on to another one. In problem number 9, the voltage across an operating 300 watt floodlight is 120 volts. What's the current through the floodlight? So here we're going to back solve. We're going to ask to solve for current. So if power equals V times I is P over V. 300 watts given and 120 volts given. Divide and you get 2.5 amps. Let's take a look at another one. Here in question 11, while operating at 120 volts, an electrical toaster has a resistance of 15 ohms. What's the power used by the toaster? So again, we're looking for power. So you go to the reference table and you look for a power equation that has volts and ohms. And you find this one. P is V squared over R. And you simply substitute 120 volts squared divided by 15 ohms is 960 watts. Notice volt squared per ohm is also a watt. Very interesting. All right, let's take a look at another one. In problem number 12, an electric iron draws 5 amps and has a resistance of 20 ohms. The amount of energy used by the iron in 40 seconds is. So we're looking for the amount of energy, so that's a W value. Now, we can go directly to W equals power times time, but the problem is we have to find electrical power. So recalling from the reference table, you'll see in equation E8, W equals power times time, but it's also expressed as VIT, I squared RT, and V squared T over R. So what variables do we have in this problem? Well, we have current, amps, which is I, and resistance, R, which is in ohms. And of course we have time. So we're going to go right to energy equals I squared RT. Put in the I, 5 squared times 20 times 40 seconds, 20,000 joules. All right, let's take a look at the next one. Here in problem 13, the the total amount of electrical energy used by a 315 watt television during 30 minutes of operation is. So electrical energy is always W, that's work. 315 watts, that's power. And 30 minutes is time, but don't forget, you have to convert 30 minutes into the number of seconds. So 315 watts times 30 minutes times 60 seconds per minute, cancel your minutes, and you get 5.67, 10 to the 5 joules. Let's take a look at another one. In problem 15, an electric dryer consumes 6 times 10 to the 6 joules of electrical energy when operating at 220 volts for 1.8 times 10 to the 3 seconds. During operation, the dryer draws a current of how many amps? Well, first of all, what information is given here? In yellow, joules, that's a W value, that's work. In purple, that is volts, potential difference. And then green is time. So we have to find an expression where we have work equals potential difference, or voltage times current times time. And we have that here on the reference table. And we solve for I, and we plug in the given values, W on the top, divided by volts times time, and you get 15 amps. It's that simple. Okay, let's move on to another problem. In problem 29, an electrical appliance draws 9 amps of current when connected to a 120 volt source of potential difference. What is the total amount of power dissipated by this appliance? So we want power, and we have to look at the choices for power formulas. And we know that power from equation E7 can be equal to V times I, or I squared R, or V squared over R. So looking to see what's given in the problem, we have a current value and a voltage value. So we'll use the VI, and we multiply together, and we get 1100 watts. Okay, let's take a look at one more problem. I saved problem number 14 for last because I really wanted to talk about the different kinds of units that can be found in electricity, and none of them are intuitive at all. The question asks, which combination of units can be used to express electrical energy? And of course, out of these choices here, you have volt coulomb, coulomb volt, volt times coulomb, volt coulomb second, and that gets very confusing. So I want to take you through this step and then do a little extension on a lesson on all the kinds of units. So what do we need to remember first? We need to remember that work is in joules. So potential difference is the work done per unit charge, which is joules per coulomb. So a joule per coulomb is nicknamed a volt. We also know that current is the rate of charge flow over time. Coulombs per second, those are an amp. And we know from Ohm's law that resistance is potential difference divided by current. So that's volt per amp. But we learned that a volt is a joule per coulomb, and we learned that an amp is a coulomb per second. Now if we put those on top of each other and flip and multiply, we get joules per coulomb squared. So let's take a look at the actual problem itself. Electrical energy equals volts times amps times seconds. So that's work. So it's V, I, and T. See, here's the expression, V, I, and T. Volts, current, time. A volt times an amp, but an amp is a coulomb per second. And multiplying that by seconds cancels these two out, and you get volt coulomb. So that's how this particular problem is solved. Let's just take a look at the mess of units that we can have here. Work is in joules. Work equals power times time. Power is in watts. Time is in seconds. VIT, volt, current, time. Volts, amp, seconds. Now, real quick, you could see that a volt times an amp is coulomb per second times a second. These two cancel out and you get volt coulomb. So that's another way of expressing it, a volt coulomb. Now let's look at I squared RT. I is in amps and they're squared. So it's coulomb squared per second squared. And ohm is omega. And seconds cancel with this seconds, leaving you with coulomb squared omega over second. The amount of electrical units that exist because there are so many common units and base units. And there are many ways in which they can be jumbled up. So the simple trick is to do what I'm doing here. start with the three basic triangles. Here are the three basic triangles: the current flow triangle, the potential difference triangle, and the Ohm's law triangle. If you know these three basic triangles and the units that go with each one of these, then you can derive, like I did here, the different unit combinations that appear in each of these expressions, whether it be for work or power. All right? This is a very tricky problem, but it's not difficult. I hope you enjoyed today's lesson, and we'll see you in the next video. Thank you for watching.